Alright, we are going to do an example problem in section 5.4, the summing amplifier. Now, if you look at this, here is the simple example problem in section 5.4. A very, very straightforward problem. We're going to begin with this. Okay. Now, let's see what it has is the configuration of a summing amplifier. Okay. If you remember, Professor Aguilar just described the way to analyze a summing amplifier. Okay. So that is what he described to us. That's exactly what we have here. Okay. Pay attention. We have a feedback, a negative feedback, that is the output tying back into the input. Okay. Then we have three inputs, VA, VB, and VC. All the three of them are feeding into the negative terminal of the operational amplifier. Okay. That's exactly the problem that he analyzed for us. Now, let's see if we can solve this problem. All I'm going to do is to simply apply the formula. Okay. There is not a whole lot of analysis in this. Also notice that the positive terminal is connected to the ground. So that's exactly what we saw. Now, if you look at this, there are two parts to this problem. Okay. The value of VA is given to be some number. VB is given to be some number. And then VC is given to be another number. Okay. Now, we are asked to find out V0 in the first part of the problem. Let's see if we can do that. Okay. And the second part of the problem gives you a value for VA, gives you the value for VB. Okay. VA and VB are given. And in addition, you are asked to find out the range for VB. VA and VC are given. Excuse me. VA and VC are given. And you are asked to find the range, meaning VB maximum, VB minimum, such that the op-amp does not saturate. Okay. We want to make sure that the op-amp does not saturate. So let's look at those problems. So solution is here. Okay. The solution is pretty straightforward, at least to the first part of the problem. I'm not going to do a lot of analysis. I'll simply write the expression for V out, VO, which is given by the formula negative of VA times RF over RA, right, plus VB times RF over RB plus VC times RF over RC. Okay, that is the expression for our output voltage, VO. Okay, now it's just a matter of plugging in the numbers. We know the value of VA to be 1.2. So let me plug those in. VO is negative. VA is given to be 1.2 volts times RF is 220K divided by RA, which is 33 kilo ohms, sorry, 33 kilo ohms. Okay, plus VB is given to be negative 1.5 volts. Okay, VB is given to be negative 1.5 volts. RF is again, this guy is RF, right? RF is 220, okay, kilo divided by RB. This guy is RB, right? RB is 22 kilo plus VC is given to be 4 times RF is 220K over RC. RC is given to be 80 kilo ohms. Okay, 80 kilo ohms. So plug those numbers in, put them into your calculator. You will see that VO is actually negative 4 volts. Okay. Now, by the way, what problem number is this? This is problem number 5.12 from the textbook. Okay. Textbook 5.12. Okay. That's the output voltage. Now, let's see. We are supposed to calculate. So that's the first part of the problem. That's it. All you have done is to recall the equation. Just 2 steps to this. Okay. Recall the equation. VO is negative 4 volts. Okay. So we have recalled the equation that Aguilar has given. That's the first part of the problem. The second part of the problem is just as simple. Okay. The second part of the problem is also pretty straightforward. Now you see VA is given. I'm going to rewrite some part of it. VA is given to be 1.2 volts. VB, we are supposed to find out a range for it. VC is given to be 4 volts still. Okay. Now, we are supposed to find out the VB range, meaning the V output maximum, VB maximum and VB minimum, so that the op amp does not saturate. Okay. So, we are still going to go back to this equation. Okay. We are still going to go back. As a matter of fact, I'm going to copy that whole equation. Okay. And paste it over here. And the same thing for the purple equation as well. I'm going to duplicate it and then copy paste it over here. The only thing that's changing is VB here. Okay. I don't know the value for VB. That's what I'm supposed to find out, the range. Right. So I'm supposed to find out the range for VB. So I leave VB as a variable because it's not given anymore. Now let's see. That's VB that we want to find out. Manipulate these numbers a little bit more. VO is negative. All of this term evaluates to 8, I think. How do I know it is 8? So it evaluates to 8 volts. Okay. So both of these go in the numerator and the denominator are multiples of 11. So 11 3s and 11 20s. Okay. And 3 goes into 1.2, 0.4 times. So 0.4 times 20 is 8. Okay. So that's the expression there. That's the simplification there. Plus, I'm going to leave VB as is, and all of this goes to a factor of 10. Okay. 22 multiplied by 10. Plus, now we can simplify this. 80 to 11. So this is going to be a factor of 11 here because 4 multiplies 80 by 20 times. Okay, therefore we have a factor of 11 there. Okay, so it's just a matter of simplification. Okay, numerical simplification. Okay, there you go. VB times 10 plus 11. Okay, this guy evaluates to be 11. This guy evaluates to be 10 times VB, and this guy evaluates to be 8 volts. Don't trust me? Plug them into your calculator. Okay, now let's see. V output, again I'm going to simplify this, is negative 11 plus 8 is 19 volts plus 10 times VB. Okay, now if you think about it, we are supposed to calculate the range for VB. Okay, VB maximum and VB minimum before saturation. Okay, so the idea is this guy, okay, so negative of 19 volts plus 10 VB should be in between the power supply voltages. Okay, it should be within the power supply voltages. That is when it is in linear region, right? That's all there is to it. Whenever they ask you to calculate a range, all you have to do is to put the output expression within this inequality. Okay, it should lie between the power supply voltages. Okay, what are the power supplies? You see, the plus VCC is 6 volts, that's plus VCC. The negative VCC is negative 6 volts. Let me double check. There, correct. Okay, plus VCC is that guy and minus VCC is negative 6. So all we have to do is calculate this expression, negative VCC, okay, less than or equals to negative 19 volts plus 10 VB less than or equals to plus 6 volts. Okay, so let me take these inequalities one at a time. 19 plus 10 times VB should be greater than or equals to negative 6 volts. Okay, so 10 times VB is greater than or equals to negative 25 volts. I'm taking 19 to the other side. It becomes negative 19. So 10 VB should be above negative 2.5 volts. Okay, so that's one condition. Okay, let's evaluate the other condition, which is simply taking this side of the inequality. Okay, 6 volts should be greater than or equals to negative of 19 volts plus 10 VB. Okay, multiply by negative 1 on both sides of the equation. We have negative 6 volts. Now less than or equals to, because we are multiplying, we change by negative 1. We change the inequality. 19 plus 10 VB. Okay, so 10 VB should be greater than or equals to plus 6 volts, negative 19 volts. 19 volts plus VB should be less than or equals to what happened here? Negative 19 plus 10 VB should be 6 volts should be greater than or equals to 19 volts plus 10 VB. So multiply this both sides by negative 25 is what we get. here we are. That's the problem. Okay. So let me go back this guy. Okay. So before I go on to the next problem, I see what the issue was. Okay. Now, I forgot a negative term in there. Okay. Negative 6 volts. So when you are talking about this inequality, negative 6 should be less than or equals to, that's exactly what I have here, negative 19 volts plus 10 VB. Okay. I should have incorporated a negative sign in there. Okay. There it is, negative sign. Now what I'm going to do is multiply both sides by a negative 1. 10 VB should be less than or equals to 6 volts. You see? Now that makes it 10 VB less than or equals to, take this guy to the other side of the equation. You have 6 minus 19, which is 13 volts. It will tell you that VB should be less than or equals to negative 1.3 volts. Okay, that is one bound. Okay, that's one side of the range for VB. Okay, now the other expression is something that we can get from here. Okay, so let me write it down. Negative 19 volts plus 10 VB should be less than or equals to plus 6 volts. Did I copy that right? Now, multiply both sides by negative 1. We have 10 VB plus 19 should be greater than or equals to negative 6 volts. Okay. Now, that makes it 10 VB should be greater than or equals to negative 25 volts. Okay. So VB should be greater than or equals to negative 2.5 volts. That's it. We have the range, okay, between these two terms. Okay. Now I can write the range for VB. Everybody with me? VB should be greater than or equals to negative 2.5 volts, and it should be less than or equals to negative 1.3 volts. Okay. If this value is satisfied, or if this inequality is satisfied, we can assure that the op-amp is going to be operating in linear region. Okay, so that's all there is to it. Straightforward application of this formula. This is the formula that Aguilar gave us from his analysis. You can derive this formula, okay, by using first principles, by applying KCL at Vn, or the V negative terminal node. Okay, now in order to calculate the range, all we have done is to take this formula, the exact same formula, plug in all the numbers except VB, because we are trying to find the range for that. We don't know the range. So we leave it as VB. Then all we want to do is to really make sure that this expression, okay, the output expression, that value lies between the positive VCC and negative VCC. Everybody with me? So that's the idea of trying to find the range for VB. Okay, if your VB is between negative 2.5 volts and negative 1.3 volts, then your op-amp is functioning in linear region. Now, in the next example, we are going to look at a little bit more interesting example problem. Okay, we'll put some more numbers.